Okay, so today, class, we're talking about speech and hearing, and then also interference. So, just looking at the book, some of the stuff that we talked about yesterday, a lot of this stuff we already discussed, but one thing we noticed, we sort of experienced it, so I think that was better than just a bunch of PowerPoints. So, this was one of the claims, I believe we saw it. Most sounds are a mix or a superposition of different frequencies. We saw that yesterday, right? We saw that experimentally when we had the spectrometer, the fast Fourier transform frequency analyzer, where even in the room where there was just some shuffling of papers, people talking, we saw different spikes in different frequencies. Even when I tried to sing a single note, okay, or say a single tone, it wasn't just one frequency of sound that you heard. In fact, or maybe better off speak, I wasn't just causing the air molecules to vibrate back and forth at one specific frequency. It was actually, some of the air was moving back and forth at like 524 hertz, some was going at 525, some was going at 526. So anyway, this is the frequency spectrum. It's normally a bar chart, like we saw yesterday, showing the relative intensities of the sound. So this is a graph showing the peak fundamental frequency, and then normally if you have an instrument or even your vocal cords or something like that, you're going to get resonance at not just the fundamental, but also at mode 2, mode 3, mode 4. We call those the higher harmonics. Your brain interprets the fundamental frequency as the pitch. That's normally the dominant tone, and then I say the dominant frequency, and then these others play a role in the quality, the tone quality, or the timbre. All right. So the tone quality is what makes a note on the trumpet sound different from the same note played on a guitar. They both play that same fundamental. We mentioned that yesterday. If we were to graph the pressure versus time, this is kind of where we were wrapping up yesterday. If we were actually to graph pressure, it would look something real squiggly like this. Their squiggly is a lot better than mine, okay? But still, do you kind of see that it's periodic? Do you kind of see that it's repeating? Okay? So the question is, could you approximate that with one major wave? Yes. Sure. Wouldn't be a great approximation, but it'd be a good first start. But then we notice that it kind of goes up and down, up and down, up and down. So what you could do is you could say that what that blue pressure wave graph looks like is the combination, or it's the superposition of this fundamental frequency plus another one that maybe kind of looks like this. And when you apply superposition, add the two of them up, it follows this. This is kind of like your baseline. But then as it goes up and down, you get something that kind of follows that. And then maybe there's another frequency to make, if we need to make some adjustments to try to make it follow that path a little bit more. Maybe there's something that's maybe kind of in between, kind of like that, another frequency. And so then eventually you can try to get it so that it follows that blue line completely. If you had an infinite number of frequencies to add together, then you could get it to match exactly right. But normally, we saw in the one video, about 6 or 7 different frequencies will approach the sound that you hear from instruments. The higher harmonics don't change the period of the sound wave, okay? They just change its shape. We can see the primary period is based on the fundamental. So talking about speech, speech begins with the vocal cords. And they're kind of moving back and forth, and that's the stretched tissue in your throat. Your vocal cords can produce a mixture of frequencies, okay? And then this is kind of weird. It says, as they vibrate, the fundamental frequency, and you get a mixture of these higher harmonics, the fundamental is the fundamental pitch of your voice, but that can be changed by changing the tension in your vocal cords. If you want to sing higher, okay, then you can kind of, or go lower. You could change the tension in your vocal cords, and that's going to change that fundamental. And you're like, okay, let me see if I can do this. So I'll do it in a second. So sound then passes through your vocal tract. So it's all those cavities in your throat, nose, mouth, and those act like tubes. And there's resonance in those tubes. So it's not really the vocal cords. The vocal cords are just kind of going, you know, there's kind of like, they're vibrating back and forth. What gets the actual sound where you hear me saying hello, where you actually are able to distinguish that from the is the standing wave that occurs inside my vocal tract. Okay, and so that you get different resonances called formants. All right, so let me see if I can. We'll keep going. So actual spoken frequencies. If you say E, when you form your vocal tract to make a certain vowel sound, it increases the amplitude of some frequencies and others. So anyway, so you get these sort of patterns of the different sound intensities. You can change your mouth, and so I'm going to try to talk in a monotone voice. And I'll make it boring, like hello class, welcome to AP Physics. This is me talking at the same frequency. But then you may ask yourself, what is Mr. Goddard doing? Since he's talking at the same frequency, why am I able to tell the difference in between the words? Does anyone have any idea how there is a difference between the words if I am making everything with the same frequency? As we're kind of up and down there at the end. Do y'all see what I'm saying? How do y'all know? How did you tell? How could you?
Your mouth shape.
My mouth shape, okay, but what did that change? I mean, what's the difference between saying
like
and buh?
We have the same fundamental frequency, but then there's the smaller ones that change the words, wouldn't it?
Yes, the smaller, yeah, those higher harmonics also do change that. As well as, you know, when I'm, you know, like the or the buh, I mean, it's that what you do with your mouth and your lips and your tongue and your teeth and all that on your nose, you know, all that makes a difference. Okay. Audio mixing. Anybody ever done any audio mixing? Emily has. Have you ever seen like in the back of like a concert? Somebody sees like a church. There's the soundboard, right? And you've got normally you've got all the different frequencies, okay, or I mean all the different channels because you have different things coming in. You got something from this microphone and that microphone and this guitar and this drum and stuff like that. And you've got all those, and you can change it. But what the thing is, each one of those lines that are coming in, which are normally called channels, you also can adjust the highs, the lows, and the mids, right?
Mm-hmm.
And you ever have that in your car? You get your treble and your bass, and you can turn up the bass or whatever. Okay. Well, the bass is the lower frequencies. Okay. So let's say that there's a sound wave. Let's say you're listening to a song, and this we take a snapshot of the frequency spectrum. Try to use it. Okay. And it looks like this. Whatever. Here's lower frequencies. Here's your higher frequencies. So just one moment in time, snapshot. This is what the sound wave looks like. You've got some different frequencies that are present. You pass it through a filter. Maybe it's a bass booster. Okay. What it does is that bass booster will take those lower frequencies, okay, and their relative positions and bump them up, okay? So notice this one's here, this one's here, this one's here. It'll bump up this frequency to here. It'll bump up that frequency to up here, and it'll bump up this frequency to right here, so that there's a higher amplitude on those lower frequencies. If you turn down the highs, which are normally like your vocals and things like that, then maybe it will turn, make this one down here. And this one, relative to this frequency here, will still be higher than it, but it will be lower than what it was initially. So we've turned down the lows, or we've turned up the lows, and we've turned down the highs. Okay, and the mids we decided to just keep the same relative position. Okay, and so that's what your audio mixing can do. Have you ever seen like the thing where we used to have this one stereo that it had all these little bars that were kind of moving up and down? Have you ever seen anything like that where they go like doo, 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 and then some of these are kind of going like doo, 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 and then there's opinions that are like doo, 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 doo. Anyway, that's normally you can get a visual on this where it's kind of showing you the relative intensity of your low frequencies, or your high frequencies, or your medium frequencies. And so, anyway, you can do all kinds of stuff like that. And if you've got, you can train your ear, but you can, to hear, to focus in on what needs to be done. And you might say, why don't we just bring them all up to the same level? Well, if you bring all frequencies up to exactly the same level, then, in music terms, I think they say it sounds flat. There's no real emphasis on that, on one or the other. Anyway, so that's some interesting things. You can do this electronically, and I think we said, and we'll watch a video here, but I want to explain what's going on in the video before we watch it. So if you're at a sound mixing board, you can change that. You can manually change this. If you're in your car, you can manually change the lows and the highs and stuff like that. But any software that plays music can have its own filter, okay? And so, and any music itself is going to it'll look at the actual spectrum of the sound that's on the MP3 file, and it could play it just as it is, or it could put some sort of filter on it. In the video that we're going to watch, the guy's going to explain that there is this Beats software. Now there's the Beats headphones, but there's one of the things that really makes the Beats headphones great is that they have a filter in there which intelligently changes the frequencies to have a better music experience. Okay, so some really, and you're like, who cares about that? Well, I don't know. How much do those Beats headphones cost, Kevin?
$300.
Like $300. There, people will pay good money for people that know how to design and build quality audio equipment, just for fun, or for recording studios. I mean, this is big business, and so if you're kind of looking at it from the smallest level, the lowest level, the physics level, everything else that is just built up. All right, let's talk also, speaking of headphones, we can talk about those noise-canceling headphones of yours, okay? Did you read about that?
Yeah.
Okay, pretty cool, huh? So one thought is, if you have a speaker here playing sound, and that's going to be represented by the yellow sound wave here, and the sine wave, and then if you have another speaker playing that exact same tone, that exact same note, sound, frequency, and if you're spaced exactly one wavelength behind it, then by the time this one catches up to this one, then they're both playing at the same, and actually it'll sound even louder. All right. Otherwise, if they're off a little bit, can we get it off? If this speaker is exactly half a wave length behind, all right, then look what happens. By the time this sound wave gets to this speaker, and then this speaker makes it sound, he's sending out a peak while the other one has a trough. So what's going to happen with those two sound waves? They'll cancel each other out. Okay? And what you hear over here is nothing. Now, it would be great if sound waves always traveled, like this is a two-dimensional representation, okay? In reality, when there's sound that would leave the speaker, it's not just going to travel along this line, it's also going to go travel along this, and it's going to travel out here, and it's going to be traveling that way. So, I mean, like, if we literally had a two-dimensional person, Arthur Square here in Flatland was able to hang out here, and he would hear it, he would hear nothing. But for you over here in Sphereland, you would hear it because this sound's going to be bouncing off there and there and there. We can simulate this, though, if you have headphones, because then essentially it's all in one line, okay? Everything's kind of coming into your ears, okay? So, this is how, do we have a picture? We don't have the picture. Throw a straw right there. This is how noise-canceling headphones work, okay? On the, here's Kevin's head. He's smiling.
It should be bigger, Mr. Goddard.
Oh, oh man, burn. Okay, all right. So here are the headphones. Okay. Kevin, you make sure I'm still in the frame with the the video.
Like
okay?
my head.
So yeah. Oh, might need to zoom out.
Oh.
All right. So Kevin wants to listen to his music. Okay. So the music's coming along there, no problem. Right there. There's the sound wave. It's going into his ears, no problem. Up, down, and it's right there. But unfortunately, there's some construction outside. Okay. And outside, there's there's this sound. It doesn't look like very. Anyway, there's sound coming in this way, and even though these headphones are well insulated, okay, that sound is going to reach him inside his ear. In fact, by the time it goes through the insulation and the time it goes here, it's going to be somewhat diminished, but it's still going to go in there. It's also going to go to his cheek, apparently. All right. But anyway, it's at a lesser amplitude because some of that energy gets transferred into the headphone. But what these headphones, they're so smart. They have like a little microphone right here, and it is doing the analysis, and it's saying, "Whoa, I'm getting a sound wave that looks like that." And by the time it gets through, it's going to look like this, and that's going to mess up what Kevin is listening to. So I'm going to actively send some extra sound to him. I'm not just going to send this green sound wave. I'm also going to send this sound wave. In retrospect, I should have drawn this much bigger, but can y'all see that? You see the red? The red is exactly the same frequency that this incoming sound wave is, but it's out of phase. It's been phase shifted, okay? You remember that from pre-cal? All right, so that the peaks hit the troughs and the troughs hit the peaks. And that
So like this.
jackhammer, highway, whatever happens to be, somebody else listening to their music over here, that sound that's coming into your headphones is actively canceled out by sound that it sends to you. Does that make sense?
Yeah.
And it makes a big difference, doesn't it?
Yes.
Rather than just
Normal.
rather than just normal. And if you haven't tried them, if you ask Kevin real nicely, he'll let you try on his active noise canceling headphones. Okay? And it all works because we have some really fast electronics. I mean really fast. Okay? Because think about how long it takes from the time for that sound to hit the microphone, okay, till the time that it goes through to the other side close to his ear. This is the distance that it has, okay? Sound's traveling, 343 meters per second. So it's got to move that far. Think how, okay, it's going 3 football fields in a second. How fast is, how long is it going to take you to go here? So we're talking the millisecond time frame. And within the millisecond, it has, his headphones have to break down the incoming sound because it's not just going to be one frequency, it's going to be multiple frequencies. It has to break it down and then cause the speaker to vibrate at exactly the right time and exactly the right amplitude, but out of phase of these. And it's got to be constantly listening. It's not just going to be like, okay, I got it. There you go. Done forever. It's got to be doing this continuously, right? Because all of a sudden, then somebody walks in and yells, "Hey, Kevin!" Some sort of like, it's got to try to cancel that out by basically yelling into the headphones.
Yeah,
all right. Okay. So what would be cool is if you could record what it was sending you. All right.
Yeah.
Then you're like, well, why don't? So the question is, Kevin said, why don't I hear that? Like the same sound but out of phase.
Yeah.
And the answer is because it's canceled out by this one. And remember superposition. It's really sending you that plus it's sending you your music. So those two end up adding together, and you end up with this wave superimposed on that wave. And this is what gets to his ear from the speaker, but that combines with this. Anyway, so they cancel out. Does that make sense? It's some pretty interesting stuff. you can, there are lots of calculations, and the book talks about that. We're not really going to deal with a lot of problems that deal with these, but you can think that, you can find out exactly where this sound source is and where that sound source is, and then line them up. This also comes into comes into play when you've got like soundproof rooms. There's loud spots and soft spots in the room, based on where everything reflects. Okay, so just to say that slightly different, you can get a similar effect of this, okay, just in a room, okay, because my voice is going over there to Miranda's ears, okay, but my straight line, okay, but it's also the sound waves are also hitting that wall and going that way, right? So you can imagine there's a little bit of a delay. This sound wave's going this way, then the sound wave over here hits that wall, and then it comes back, and then there's going to be a region where they meet, okay, where there's interference, where it is possible it could be completely constructive, and in that region right there, those two waves hit, and it's like woohoo, okay, they're both totally in sync. It's also possible that they get out of sync and they get completely soft, all right? So you can get loud spots and soft spots within a room based on the shape of the room and the surface that the sound is reflecting off of, because in some of those spots you get complete destructive interference or complete constructive interference, okay? And that does play a role. Let's see what else. I think we're going to watch something on that as well. You could think about it like this: if there's two sound, that was just sort of one person talking and the sound going out there. Now think of a situation where maybe you've got some sort of concert, okay, and you've got speakers over here and you've got speakers over here, and the sound is blasting out of both of them, okay? There's someone in that room, okay, that's going to be, well, let me just back this up. So imagine the sound waves are going out here as circular wave fronts, okay? And the sound waves here are going out circular wave fronts. And so they're kind of going like this, up and down. The waves are leaving here. Look at this spot right here. This is where a wave hits a wave peak hits a wave peak. All right? What's going to happen to the person? What's this person sitting right here going to hear? Peak hits peak.
Oh,
It's
too much, a lot.
It's going to sound even louder. Okay. What about like right here, where peak hits trough? Oh, sorry. Yeah, peak hits trough.
But it would be
Cancel.
It would. All right. And if this was totally flat situation, then that person in a concert here would hear nothing.
But since they
Okay.
have like the.
But since it's bouncing off all the different walls and stuff like that, and things like that, yeah, you do hear. But you do hear some loud and soft spots. If you remember, we watched that one video of the guys that were like in, I don't know, Holland or something like the Netherlands or something. They were in Europe and they had the two-dimensional Rubens table.
Oh,
Rubens tube. He's like, oh, I got a node and I got an anti-node, and because he was going around different spots in the room, and his microphone on the camera was picking up loud spots and soft spots where there was constructive interference and destructive. And it wasn't, the soft spots were not totally quiet, okay, but they were it was reduced. Okay, we'll talk about Beats tomorrow, not the Beats by Dre or the Beat headphones or whatever, but other type of Beats. Go and hit the lights. And also you can stop the video. They can watch the videos. It's just crazy.